This video is about standard form and prefixes. Often in physics we'll find ourselves using very small or very large numbers. For example, here we have the elementary charge, here we have Planck's constant, and below that we have Avogadro's number. Writing the numbers and keeping track of all those zeros can be a challenge. So instead, we often write our numbers in standard form, also known as scientific notation. In standard form, a number is presented as a significand multiplied by some order of magnitude, some power of 10. Let's take the first example, the charge of the electron, and we'll write this number in standard form. The significand is any number that is equal to or larger than 1, but less than 10. So to four significant figures, for example, our significand is any number from 1.000 to 9.999. The significand starts with the first significant figure, which in this case is 1. And the next three significant figures are 602. So our significand will be written as 1.602. You will notice that that has the same number of significant figures, 4, as this very long number here, because the zeros beforehand are not significant. The decimal place has to be moved 19 places to the right to make this number the significand. That means if we multiply the significand by 10 to the minus 19, it gets us back to this number here. So you can see the elementary charge can also be written as 1.602 times 10 to the minus 19 coulombs. That's standard form. The number could also be written as 0.1602 times 10 to the negative 18 coulombs. And that's correct, but it's not standard form. Or we could write our number as 16.02 times 10 to the negative 20 coulombs. And again, that's a correct number, but it's not standard form. Remember, for standard form, the significand, or mantissa, should be equal to or larger than 1, but smaller than 10. Let's write Planck's constant, which is the next one on the list, h. Let's write that in standard form. Well, we can see that the first significant figure is 6, and so we can write this number as 6.63 times some order of magnitude. Well, we have to move the decimal point 34 places to the right to get this number to be a valid significand. So our number is 6.63 times 10 to the negative 34. Again, the significand is equal to or larger than 1, but less than 10. And that is a lot more convenient to write the number in this standard form. Avogadro's number is one of the larger numbers we deal with in physics. And here, although I haven't drawn it, the decimal point is on the right. So, first of all, the first significant figure is 6, and then we'll write this number to 3 significant figures. You can see in standard form it's very easy to see how many significant figures your number is written to. If I were to write 6.020, that would be a 4 significant figure number. But we're going to write 6.02, that is a 3 significant figure number. We have to move the decimal point 23 places to the left. So this number has an order of magnitude 10 to the 23. You'll see that the numbers where I've written zeros are grouped in 3s. That makes it easier to count how many places your decimal point has to move, and it will become useful when we look at unit prefixes in just a moment. Avoid commas, because in some parts of the world, in fact in most parts of the world, the comma is the decimal point. Here are the unit prefixes that you need to learn for your A-level. And I'm not going to be using centi for this, because it doesn't follow this nice, easy to remember pattern. But it does also exist and slots in between kilo and milli. You will notice that the orders of magnitude go up in 3s. Or if you go down the list, they go down in 3s. With the exception of kilo, all those that have a positive order of magnitude have capital letters for their prefixes. And all those that have a negative order of magnitude have lowercase letters. Watch out for micro. That's the Greek letter mu. Also look out for peta and pico. Peta is a capital P, pico is a lowercase p. Let's choose an appropriate prefix for our charge of our electron. The order of magnitude part here, 10 to the power of negative 19, can be split into 10 to the power of negative 16 times 10 to the power of negative 3. You can see that 10 to the negative 16 times 10 to the negative 3 is 10 to the negative 19. Well, we could replace this 10 to the negative 3 with milli. And thus we've presented our elementary charge in units of millicoulombs. 10 to the minus 19 is also 10 to the minus 13 times 10 to the minus 6. And 10 to the minus 6 is micro. In fact, you can see that I'm reducing the order of magnitude by 3 each time. Or in fact, I'm increasing it because it's a negative order of magnitude. And then I'm going down this list. 10 to the minus 9 is nano. So my elementary charge in nanocoulombs is 1.602 times 10 to the negative 10 nanocoulombs. I've just replaced the 10 to the negative 9 with nano. And here we are at the bottom of the list now in femtocoulombs, but the list does go further. Below femto is atto, so I could write this as 0.1602 attocoulombs, and it would be perfectly correct. And in fact, below atto is zepto. So adding 3 onto this order of magnitude again, I get 10 to the power of 2. So this is 160.2 zeptocoulombs. The most appropriate prefix would be the prefix that gives you the easiest number to handle, which I would say is either 0.1602 attocoulombs in this case, or 160.2 zeptocoulombs. Of course, all these numbers are correct.